So in this presentation, we're going to talk about acids and bases reactions, specifically Bronsted-Lowry acids, conjugates, and also the strengths of acids and bases. And I want you to really think about why is it that we have these acids and how they react in a chemical reaction. So start off with acids they taste sour. Specifically, they are found in citrus fruits and also they are found in things like vinegar. In fact, we actually encounter acids more often than not across the board in many of our foods that we eat. Bases taste bitter. Some of them are actually poisonous. In fact, people actually reject this flavor in many cases for a very good reason. Because through evolutionary processes, our ancestors at one point died from eating bases. So it's kind of interesting to see that, plants have this ability to create bases, and that we've evolved the ability to reject bitterness. Broccoli, turnip, and baking soda are classic examples of something that tastes bitter. In fact, if you take a look at a lot of these vegetables, they do have these in there so that people won't eat them or animals won't eat them. Bases, for the most part, feel very slippery. Now, think of soap as an example. They usually react with your oils to form soap, and they are found in many cleaning products, specifically things that have ammonia in it. So if you take a look at your kitchen cabinet, you're going to find a lot of bases. They're also found in blood, and also drain cleaner contains potassium hydroxide. So a lot of interesting applications for bases. Most of them are going to be industrial cleaners. All right. So let's go ahead and define acids and bases by the Bronsted-Lowry acid. Now this is going to be what's going to be tested on the EP. So make sure you understand the definitions and also what it looks like. So a Bronsted-Lowry acid basically involves donating hydrogen ions. And these are usually going to be things that fall off the acid. While bases are going to be considered the ones that accept the H, and these are going to be the ones that accept the H plus ion. Now we're going to be talking about the H plus ion more in detail because that's what's going to drive these chemical reactions. So here's an example of a Bronsted-Lowry reaction. So specifically, as you can tell, if I denote an acid as having a hydrogen, in other words HA, and I introduce a base as B is going to accept a proton. When it does that, the H is going to transfer over to its conjugate. Now we call it the conjugate because it's going to be what it becomes. So if I take a look at the base as an example, it's called a conjugate acid of B. And now it becomes BH+. So in this specific case, you can see that the base has received the H from the acid. Likewise, if you take a look at the HA has donated a proton and now becomes an A-. So when we're talking about the conjugates, we're talking about what's the opposite of whatever it came out from. So in this case, it's going to be the conjugate base of HA, while BH is going to be the conjugate base of the base. So as you can see from here, we do have that ability for these acids and bases to change the moment they release those protons for each one. So what is what over here? So let's take a look at this example with HNO2 aqueous in water. And always you want to denote that whenever you're taking a look at Bronsted-Lowry acids and you're taking a look at protons being exchanged, you're always going to find that these examples always give way to what's going to happen on the right hand side. So we denote that by the acid and the base as being the acid is HNO2. Now again, you do have to know these acids, so it's very important that you memorize the list of acids that would best fit this so that you don't have to think about what's the acid. Water is amphoteric, so it can react as both a base and a water. So in this case, it's the base. And as you can see from here, you're going to form your NO2s, or we're called the nitrites. And so your H3O is going to be your base because it has received that proton. So now that's going to be called your conjugate acid, while your conjugate base is considered to be the one that lost the H. Now in this specific case, we have ammonia. Now ammonia is an H3 and water here, so we already know that ammonia is a base. And in this case, water is acting as an acid, again, being that amphoteric reaction. By getting the NH3, now what we're going to see here is that the acid from the H2 is going to donate to the NH3, forming NH4. Now remember, this reaction is also reversible, so you can go back and forth because it could actually create those. And again, we have OH-, and so water can act as an acid or a base. So this in case, we're going to see that it's a conjugate acid and it's going to be a conjugate base. By looking at this reaction, we can automatically know these types of situations. So water in acid-base reaction usually plays a very large role in many of this. So if I take a look at water as an example, water exists as an aqueous solution because it can accept or it can donate hydrogen ions. So if I take a look at H2O plus H plus, water can form H3O. And H3O is called hydronium. And the hydronium is an ion, and the reason why it's because in this case it has accepted a proton. By accepting that proton, it's technically having an H3O positive charge. However, if it loses an H, in this case it becomes an OH or a hydroxide, and it releases that H plus in there. So in this case it becomes kind of like an acid. So a hydrogen ion can be pulled off of water, which leaves the hydroxide with 3 lone pairs around the oxygen atom, as you can see from this Lewis dot. So let's talk about conjugate acid-base pairs again. So if I take a look at an acid-base pair, we already know that if you take a look at the conjugates, like for example HA and B, you automatically create the conjugate acid-base pairs by moving those acids H's in and out. Alright, so let's talk about acid strengths. So acids are generally described by the degree of ionization that they have in water. So if I take a look at HA and H3O, I want to know how much of it has ionized into H3O and A-. If I get 100% ionization, what I do get is H3O positive and A-. And what that really means is that you have free-flowing ions in the liquid. So as an example, if I take a look at HA, it's going to donate that H to H2O, making hydronium, and now that's going to get A-. Now what happens here is it's a one-way equilibrium, so which means direction. So the equilibrium has to fall under a certain direction. We'll talk about equilibrium later on, but basically if you take a look at these reactions, if I give you a weak acid, in this specific case like something like HA, like a weaker acid, you're going to see an equilibrium that lies to the left or to the middle. In other words, you're not going to get much of this. So when we're talking about equilibrium, what we're talking about is how much production you're producing of your products. So if it lies to the right, that means I'm producing a lot of the H3O, which means the ionization is high. It means you're getting a lot of those ions. If the equilibrium lies to the left, that means I'm getting partial ionization. In other words, I'm not getting a lot of that ionization, which usually means it's a weak acid. So here are your big sixes, and make sure you write these down and make sure you remember what they are. So these are going to be the ones that ionize, so you need to memorize them. So HClO4, HI, HBr, HCl, HNO3, and H2SO4. Now remember that these are all in the halogen family. So I like to look at it as group 17, acids, and basically your polyatomics, which are sulfates, and your ClO4, which are chlorates. Now strong bases usually are going to have a hydroxide, and these are going to involve group 1 cations and also calcium, Sr, and barium, or strontium and barium hydroxides. So all of the group 1 people, all the group 1 elements plus group 2 with calcium, strontium, and barium have strong bases. So remember those as well. Now, how do we make an acid strong or weak? So strong acids always have a weak conjugate base. So if I give you something like a hydrochloric acid, it's going to form a Cl- anion that's going to be fairly weak. Very weak acid is going to have a very strong conjugate base. So the example here is acetic acid. Acetic acid is really weak acid, but once it gets into its conjugate, it's going to be it's the acetate ion. It's going to be a very, very highly, a very strong base. Acids with mid-range are going to have usually mid-range strength, so as you guys can tell from that. So here's the strength of the acid. So on the top end, the top dog, what I call it, it's going to be hydrochloric acid, the same stuff found in your stomach. Moving down the row, we have nitric acid, HNO3, hydrofluoric acid. We have NH4, we have H2O, water, and then methane CH4, which is kind of interesting because normally you wouldn't think of CH4 as an acid, but yes, it does. Bases are going to be Cl- for the strength, so again the conjugate in terms of the weaker ones. Your CH3 is actually a very strong base. Hydroxide, very strong because we talked about water being a weak acid, but it's hydroxide, it's a very, very big one. NH3, F-, and so on. So again, they're inversely proportional. So all you have to do is know one of them, you can figure out the other one. Stronger bases always accept the most protons in an acid. So if I give you an example of what makes a base strong, it's the one that picks up the most. And there are always two types of bases, the base on the reactant side of the equation and the conjugate on the right side. So again, just keep in mind this idea of conjugates, how they're losing protons and how they're gaining protons on the other side. So strong acids have weak conjugate base. So here's an example of H2O and Br-. So HBr, as you guys can tell from here, would actually donate the H, and now it becomes a Br minus. The Br minus and the H2 are going to compete because they're both in the same solution. So Br is going to say, I want that hydrogen. H2O is also going to want that. But because H2O is a stronger base, it's going to win, and the reaction goes to fullest. However, if it were the opposite sign, then perhaps maybe they wouldn't get that. So remember that in this solution, you have competition for the H plus ions. Now, a weak acid is going to have a strong conjugate. So for example, H2O and NH3, they both compete for protons. So water is going to want to pick up that proton, and then NH3, as on this side, is also going to want it. But because NH3 is a stronger base, it's going to win most of the time, and the reaction is going to go to the left. In other words, you're going to get more of your reactants. And so in that case, you can kind of predict what's going to look like if you're talking about competition between these ions. All right, guys, well, hopefully you enjoyed this. We covered a lot in terms of conjugates. Make sure you do the problem sets. We're going to review this a little bit more about this competition, this idea of conjugates, the acids, the bases, how they all kind of fit in.